Okay, well, we'll get started. So we're going to change gears a bit and start introducing basic spectroscopy. The idea is that we'll be using this as a preparation for, again, ultimately looking at sort of the basic principles between absorption and laser-induced fluorescence, which will be the next two lectures. Okay, so you'll find that these set of notes are very detailed, I think, so I don't want us to get bogged down too much. There's going to be a tremendous amount of text, but I actually did that for you guys because I knew you're taking these things away. So this is not your classical like in-class lecture where you just hate the fact that there's so much text on the overhead and you can't follow along. I actually have this so that you can take it away. So again, I don't expect the consumption of all this because there's a tremendous amount of material here, and we're going to go through it, but really just trying to get a general idea on some of these spectroscopic principles. Okay. So the goal of this lecture is to give an overview of the fundamentals of spectroscopy, not really focus on any particular diagnostic at this point, which is a brief description of energy levels, spectroscopy fundamentals, discussion of rotational, vibrational, electronic transitions, and we'll use this as a prep for laser-induced fluorescence. Okay. So what is spectroscopy? That's kind of a definition. This is a science which uses absorption and emission of electromagnetic radiation to deduce certain properties about atomic and molecular properties. Okay. So really, a lot of you have different introduction to spectroscopic techniques, whether they're absorption, whether laser-induced fluorescence, chemiluminescence, and these things are all optical versions that use spectroscopy. Large number of combustion diagnostics that we just talked about are spectroscopic based. Now, in order to get into spectroscopy, we have to kind of venture into the world of quantum mechanics. But again, I wanted these to come from a practitioner point of view. So there'll be some quantum mechanic ideas presented in here, Schrodinger's equation and solutions. But what we're going to do is mainly accept quantum mechanic rules, okay? We're going to accept the solutions. We're going to accept how you get from point A to point B, okay? We're not going to necessarily go and try to prove these or go over the intense derivations, okay, for many of these processes. So again, in terms of kind of our boundary conditions, we're going to accept the fact that there are certain things such as quantized energy levels, that energies occur at discrete levels, and that there are certain things called allowed transitions. There are certain things that are in resonance with molecules and atomic species, okay? We know that molecules have electronic, vibrational, and rotational energy, okay? And we will also accept the Born-Oppenheimer approximation as the total internal energy is the sum of the electronic, vibrational, and rotational energies, okay? So the Born-Oppenheimer approximation allows us to separate nuclear motion from electron motion. Okay, I'll come back to this in a little bit, but basically, from the viewpoint of an electron flying around, the nucleus is stationary. Okay, there's such a difference in mass and the velocities. Okay, so it allows us to parse out and treat each of these separately. Okay. And so moving from that, we'll also, again, since we're accepting that there's quantized energy levels, we know that molecules can only rotate and vibrate at discrete frequencies. And the frequencies, these are just energies. Okay? So all of these we're going to accept kind of as the basis for how we work through our basic spectroscopy. So if we accept the Born-Oppenheimer approximation such that we can write our internal energy as the summation of the electronic, vibrational, rotational energies, we have to give these kind of some nomenclature or some terminology that's used. We typically refer to an electronic system, a vibrational band, and a rotational line. Okay? And so this is what you'll hear me refer to. We may excite, some molecule, the Q6 rotational line of the V'1 vibrational band and the, eta X electronic system. Okay? And we'll go over nomenclature in a little bit. So this is a potential energy curve for one electronic state. You can see we're going to have the ground state, and we'll talk about each one of these. And then we're showing the first electronic excited state. You can have multiple electronic excited states. Okay? So this is, within here, we can have a transition between electronic states. We'll talk about this at the end of the lecture, say going from this what we refer to as T double prime to T prime. We can, within electronic state, we can have various vibrational energy states here, V prime, V prime, 1, 2, 0, 1, 2, 3. The vibrational energy states give the electronic state its fine structure, okay? We start with nomenclature that V equals 0 is the lowest vibrational frequency, and V is greater than 0 correspond to higher vibrational frequencies. Now, for any given vibrational band, we can have rotational energy states that give now the fine structure to the vibrational bands. So again, the vibrational bands are within the electronic structure, and now we have the rotational structure within the vibrational bands. Okay? For these, J is equal to 0 is the lowest rotational energy state, and J greater than 0 corresponds to higher rotational energy. Okay? So right now, hopefully, we're just getting kind of some nomenclature out. We have an electronic system, vibrational band, rotational line. Rotational line gives the fine structure to the vibrational band. The vibrational band is the structure, it gives the fine structure of the electronic system. We will initially talk about these separated, but then we have to understand since the rotational is embedded on the vibrational, we have something called row vibrational coupling. Okay, so let's talk a little bit about energy levels. So line positions, i.e. from a practical point of view or a practitioner point of view, the place where you would want to tune your laser, if you will, are determined from the difference between energy levels. Again, the energy levels are discrete, and therefore spectra are discrete, and in certain they're optically allowed. So when I say discrete, that means their location. This whole lecture is going to be on the x-axis. You'll see what I mean by that, and the next lecture will be on the y-axis. What we're trying to do is determine where these things lie in spectral space. Their center frequency is allowed only at discrete locations. Now, the reason why you can get like a continuous is that's due to broadening in line shapes, and we'll talk about this. But energy levels are discrete, and therefore the position of their lines, where they're rotational and vibrational, are discrete as well. So let's look here at, here's an example of a potential energy diagram for OH, and we'll use an example of OH absorption, because many of you have used OH absorption here, or you have looked at fluorescence, which is, we talked about as absorption plus re-emission of the photon. Okay? So if I take a look at a spectra, I'm trying to connect now the spectra to the energy levels. If we look at the 0-0 band, and we'll talk about what this means, this really means that we're going from the V equals 0 in the ground state to V equals 0 in the upper excited state. This occurs at a transition near 310 at 306, right? Now, if we look at 1-0, where we go from a transition from the 0 vibrational band, the vibrational band 0 in the ground state, up to the first band, this requires this amount of energy, which will give us our sort of well-known 282 line, and we can continue on, okay? So what happens is that hopefully you're making the connection now is that this difference in energy to excite it from one vibrational band to another determines the approximate location of where you need to tune your laser. And this is connected back to what we did in the first couple lectures, that you can show that delta E can be converted to a wave number and a wavelength. Now within a given vibrational band, we can now look at a very detailed rotational structure. Okay? And again, these each will be determined, these are at discrete positions, and which rotational line you would want to excite, you would have to tune to that exact energy difference in the molecule. Okay? Now, one thing I'll point out is that these are electronic. If you've done PLIF and worked in the UV with low H, or even any of the other ones, CH or NO. These are typically electronic transitions, and therefore that's why these spectra are very complex. We'll start out with just simple rotational, vibrational, non-electronic contributions, and you'll see the beauty in those spectra. Okay. Okay. So let's start again with our representation of the energy states for the valence electron of a diatomic molecule. We have our OH potential curves. So the first thing we want to think about is how we draw, let's talk about a simple diatomic. Okay? What you can imagine is we can describe ours the way that we want to think about just something, we want to keep this kind of picture in our head. We have two nuclei, and we're surrounded by an electron cloud. Okay? So what happens if we start talking about vibrational energy, we'll talk about, again, we can think about these things being moved back and forth. Vibrational energy is quantized, so if we go to one vibrational level, whatever it is right now, they're separated by some distance, capital R. Let's make sure they can be separated by what we'll call a vector because it can be in space, and we need a coordinate system of lower r. Okay, so the reason why this is a vector is you can imagine that this is also rotating at the same time, so this can be in any three-dimensional position. Okay, and the r can change because the actual position between the two nuclei can change. Okay, so let's start looking at this, is that for any given level, the two nuclei oscillate within the potential well. What we can think about this is when we're at small r, the positive nuclei repel each other. They get closer, they try to send each other apart. But as they get too far apart, negative electrons attract the positive nuclei and bring them back so that they don't separate. Okay? We don't want separation. So this is what generates the idea of vibration. The molecule starts to vibrate. So our vibrational energy is going to be characterized by the vibrational quantum numbers. V double prime is going to be our lower state, also called the X state. Okay? And then our first excited state would be V prime. Okay? And this is for OH is the A state. Okay? And these typically for electronic transitions will go A, B, C. They'll go up. Occasionally, there are molecules that have been, they end up finding a lower one later, and therefore you'll find like A, B, and then C. But in general, they work their way up. Okay? Now the molecule also rotates. Rotational energy is quantized as well. Okay, so the frequency at which it rotates is also at discrete values. And the rotational energy is characterized by rotational quantum numbers, J double prime being the lower state and J prime being the excited state. Okay, so just in kind of quick review, for any given level, we kind of have a vibrational state. We just have to understand our lower states are going to be these double primes, both for the vibrational and the J state, vibrational and the rotational, and then the excited state are the single primes. Again, okay. And then we know already that these changes in energy, whatever we induce, can be related to the optical frequency. So what we should say is that, again, coming back to this idea that if I want to induce a transition from here to here, or even here to here, right? They don't have to be electronic transitions. They can just be within a vibrational, from one vibrational state within a single electronic. And that's what pure rotational, pure vibrational spectroscopy is. You stay in a single electronic state, and you can just look at the energy difference here, right? And then that energy difference is related to the optical frequency that you need to tune to. Okay. All right, so due to the Born-Oppenheimer approximation, we can actually separate out the nuclear solutions from the electronic solution to Schrödinger's equation. The nuclear being the vibration and rotation action, okay? And we can remove this from the influence for now of the electronic solution. And again, remember, electrons are moving fast from their viewpoint. The nuclei are remaining fixed. Okay? And so what this actually implies is something else, is that the distance now, is no longer a variable parameter. It is no longer a variable, but it's now a parameter. Okay? And what that means is that we're basically thinking about from this is that from the viewpoint of the electrons, the nucleus is frozen, right? It's not moving. So it's at a fixed position, and we'll use this in our analysis. So what we can do is we can solve for rotational and vibrational states of the nuclei with reasonable accuracy. We can do this. I'll talk about later, it's the electronic that there's not really nice solutions for. You can do them with ab initio, but then they have so many rules that change per molecule, and they're very difficult to deal with. But for the pure rotational and the vibrational states, we can actually solve with reasonable accuracy. Okay? So again, we'll start out separately. We'll start out with dealing with vibration first and rotation then, but then we do have to couple them together, okay? And because you can imagine, as I just told you, the rotational states give the fine structure to the vibrational states. They certainly have to interact, all right? And then finally, we'll discuss the electron interactions with the nuclei. Okay, let's start with the nuclear solution. So here's the Schrodinger equation for a diatomic molecule. We have the nuclear component, okay, that has our vibration rotational end, and we have our electronic component. So what we have here is our reduced Planck's constant, so it's just Planck's constant divided by 2 pi. We have our reduced mass here between the two atoms. We have our electronic mass. We have the number of electrons, so we have to summate over all the number of electrons. We have some sort of potential interaction. We can think about this as we simplify it. This is just potential energy. Okay? R is a position vector at any point in space, and R is the nuclear coordinate, and that's the spacing between the nuclei. And then this is, of course, our wave function. Okay? So that's Schrodinger's equation. Now, using, we can actually, like I said, applying the Born-Oppenheimer, we can actually separate these out. So that is, again, the time-independent Schrodinger equation. So if we apply the Born-Oppenheimer approximation, we can actually separate out our wave function here into both the electronic contribution and just the nuclear contribution. Again, we substitute that in, and you actually end up with another Schrodinger's equation called the nuclear Schrodinger equation. Okay? And we have the nuclear wave function, psi of n. Now we've replaced this kind of generic potential interaction with the electric potential distribution, and that's an eigenvalue of the electronic Schrodinger equation. Again, we have to keep the connection between the two solutions. And now our nuclear solution only is dependent on R. Okay? It's fixed only on the separation and not on its position. So keep in mind up here, this E was the total energy of the system. That's the internal plus the electronic. So this has translation, rotational, vibration, and electronic energy in there. Okay, and we keep it in here. And what we're going to do is try to simplify this further until we get to down something that you could call the vibrational, if you wanted to, Schrodinger equation. We can then separate, again, not doing the math behind these. I want you to just see these are further separable, such that vibration and rotation can be looked at separately. When you do all that, lots of substitute working out, we can actually get down to vibration, okay, where we'll work within this equation. Okay, we have an eigenvalue equation of the Hamiltonian for just the relative motion between two nuclei. So that is vibration, right? That's what we want to look. So again, we have this V, which is a potential interaction. We can call this potential energy. We have our vibrational wave function, and we have just the vibrational energy. Okay? Now, a key to solving this is we have to choose our potential function. Okay? We have to actually choose how we're going to model the potential well of the molecule. Okay? So again, let's think about this approach, a simple way, again, to take this is, let's again, I'll draw just small, but hopefully you can see that. Okay? Is that imagine you have them just held together, sometimes called a spring or a mass. Okay? Where this actually comes from is that, let's assume you say at some over time average we have an equilibrium position. Okay? And if I do a Taylor expansion around its equilibrium position, this is what a Taylor expansion looks like, except neglecting higher order terms. Well, if you look at that, that's just a spring problem. Okay? We have our equilibrium position, and then we have 1/2 kx squared, and k is just a force constant. So really all we're doing right now for this sample is that the molecule is it's attached by a spring. It's just going back and forth across some equilibrium. We haven't allowed for any, we'll eventually allow for some distortion and things like that. But right now this is just a very simple system. If we put that into equation 97 and solve the Schrodinger's equation, we end up with the answer for the 1D harmonic oscillator. Okay? And so the eigenvalue for this is what you've probably seen in spectroscopy, is that we have our vibration level plus 1/2 reduced Planck's constant times omega E, which is a vibrational angular frequency. Okay? So this tells you this is the energy vibration at any given V. Okay? And this is the relationship for angular frequency. So the harmonic oscillator is a quite convenient approximation for diatomic molecules. And it's actually good up to about the first upper vibrational state, first vibrational level of the excited state, but then you start to have increasing amount of error. Okay? A more accurate description, instead of the simple mass problem, is something called Morse potential. It's an anharmonic oscillator. This is the characteristic form. We have a Weld depth. And what it ends up, the solution is essentially the same thing except with an anharmonic correction. Except the only thing is, if you compare, I have H here. This is just the time writing them instead of having omega. If you look at this, the other one had the reduced Planck's constant, which is H over 2 pi. So C over 2 pi times the wave number gives us the angular frequency. So this first part is the harmonic contribution that we get from the simple spring mass system. And then this is an anharmonic portion. Okay? So this is what your potential diagram looks like. We have our harmonic, okay, our simple spring mass system, and then now we have our Morse, which actually looks what potential diagram looks like. Okay? So what happens, the Morse is a better approximation of the vibrational energy structure because it implicitly includes the effects of bond breaking. Right? Because what happens is it allows you these spacing are getting closer and closer as you head toward the dissociation energy. Okay? And it actually includes, you can see it's not symmetric, so it's including anharmonicity, and all of these allow you to generate overtones. Okay? Overtones. Okay? And these are just things that you can make a note of and go look. The Morse potential just gives you a more accurate solution. And so anyway, there's our uneven spacing, and this anharmonicity, as we start heading toward the dissociation, the vibration levels are coming closer and closer together to eventually they're on top of each other and the molecule can break apart. Now, we can also rotate. So we have a solution, believe it or not. Let me emphasize on this last slide, this is the location of your vibrational bands because it's the energy. And what we'll do at the end is we put it all together, we'll actually show how we end up finding all the different lines. But we've now found the vibrational energy for any vibrational level. Okay? These are constants. Okay, nu E, these are in wave number units, but these are constants that have to be determined usually experimentally or ab initio. But now we actually have the energy of vibrational. All right, now we can rotate as well. And let's use a simple system here. Let's use something called a rigid rotor model. And why do we, again, so what a rigid rotor model is, we have mass 1, mass 2, and they're stuck between, you put two ends on, a pipe stick and you don't allow them to change. And why can we do that? We've already said things are vibrating, right? But this bond length connecting the masses is much greater than the change in bond length due to vibration. We like to do our hands like this or make these things seem like they're going out of control, right? But really the vibration is this tiny spacing compared to the bond length, okay? So since delta L is much less than, the change in bond length is much less than the actual bond length, we can say for rotation purposes that the bond length remains fixed, okay? Now, if the bond length remains fixed, the analysis is much easier. We can just say the bond length, of course, is R1 plus R2, and it rotates around some center of mass with some frequency omega rotation, okay, some angular frequency. So in order to solve this, let's start a little bit with a little classical mechanics. We know that within here, if we took a rigid system and put one mass here and one mass here, that the mass times the radius of 1 has to equal the mass of radius 2 times the mass of 2 times the radius of 2. Now what we can do is take and solve for R1, which we divide by M1, okay, and then go and substitute this expression, do some manipulation, and you can find these expressions here that relate the different radius, R1 and R2, to both of the masses and the bond length, okay? Now, then we can take and find what the total kinetic energy of the system is. The total kinetic energy of the system we know has to be a velocity times a mass. And since we have a system of two different masses, we have to take the average. So we have m1 v1 squared, where this is a linear velocity. But now we can change that out with the bond length, again, the radius, if you will, and an angular frequency. Just substitute. And we can end up writing the kinetic energy of the system in terms of the radius 1, radius 2, and this rotational frequency, okay? And so now this is still classical mechanics. We've taken a little step outside of here. We can further write, we know the moment of inertia, definition of the moment of inertia, substitute that in, since now we have the kinetic energy, T, is equal to the moment of inertia of the system times its angular frequency squared divided by 2. So we want this to simplify this kinetic energy, because what happens is you ultimately have to, you'll see, we have to write an operator in the Schrodinger equation, and once we put it in this form, it's nice and neat, and then the solution can be neatly done in about 4 to 5 pages, which we're not going to do, okay? I did this when I started developing these lectures last year. I actually did the solution, and I realized there's no way that anyone wants to sit through this at all. So we just put up the answer, right? So, but because we're trying to learn about spectroscopy, okay? Again, we can always write, we can keep playing all these equations that you learned in kinematics and dynamics in undergrad. We can keep writing the moment inertia. We can keep doing this, okay? Now, again, we can also define the angular momentum and then do more substitution. Now what we can do is actually write, well, we know the angular momentum is the moment inertia times the angular velocity. And so we can actually get this kinetic energy in terms of the angular momentum and the moment of inertia. Or, better yet, this is what we want, L squared equals 2IT. There's a reason we want to do that. So if you go back to the Schrodinger equation, but now in cylindrical coordinates, again, don't worry, you didn't miss the math. We're just now writing it in terms of cylindrical coordinates. The key is that we can change these operators. So we can define an angular momentum operator in this manner, okay? So this allows us just to rearrange our Schrodinger equation in this form. All these are the different energy. This is y. These are just in cylindrical coordinates, okay? That's part's not important. If you're interested, certainly go look up the solution. And this is the solution using, it's done via separation of variables, and a lot of frustration on my part to get here. I didn't solve this. Sorry, I shouldn't say like I made this. I mean, just to reproduce answers that are well known. But anyway, this is the solution to rotational energy, okay? Really what it is, we have the reduced Planck's constant, we have 2 over I, and we have J plus J1. And J is the nuclear angular momentum quantum number. It's related to the rotational quantum number, but we haven't taken into account any interaction with electronic transition, so it's technically a different J, okay? We'll come back to that at the end. But we can write it in terms of this B, which this B becomes a spectroscopic constant, which is then h squared over 8 pi I, if you substitute back in Planck's constant there, okay? So this is the solution. What we've done here is just showing you how you get there, not all the details, but we now have the solution for the vibrational energy. We have the solution for the rotational energy, okay? Now we have to ask ourselves, are all transitions allowed? Can I just go and, can I put in any value for J? Can I put J is equal to 0.1, J of 0.2? No, there are so-called selection rules. And so for purely rotational transitions, meaning we're in the microwave region, the selection rules that the change in J within a vibrational band has to be plus or minus 1. And if there's an electronic transition, you're allowed to have delta J is equal to 0 or plus or minus 1. Okay, so this quantizes it and allows you to show this is only the change in rotational transitions that we can have. Okay. So let's consider the selection rules in the context of absorption. When a molecule is irradiated with a laser, light source, photons, flashlight, whatever you want to give it, it may absorb the photons, okay, and undergo an energy transition. It'll absorb them only if the energy of the transition matches the energy of the incident photon. So this E has to be equal to Planck's constant times F, okay? So the energy difference for a diatomic molecule has to obey the selection rules. So our change in energy can be simply, if we take our selection rule being delta J equals plus or minus 1, we can just look at the difference of energy between J plus 1 and J, and add J plus 1 for all the J's, and that transitions, when it was J and J plus 1, that now becomes J plus 1 plus J plus 2, then minus J times J plus 1. And what your energy difference here has to be 2 times BE times J plus 1. That's what you have to equal in terms of your laser. You have to equal this energy difference. So then the actual frequency is 2B J plus 1 over H, or in terms of spectroscopic frequency, 2B J plus 1 over HC. This is the spectroscopic. That's the wave numbers that you need to tune to. Okay? And so we've now used our selection rules and the actual energy of the rotation to actually understand exactly where these frequencies are. Okay? Now the vibrational transitions also have selection rules. So for a pure harmonic oscillator, it's delta V, if you will, here is plus or minus 1. And if you add the anharmonic oscillator, it's plus or minus 1. Then you're also allowed plus or minus 2, leading to overtones. Okay? Now, we have to ask ourselves for rotation, coming back to rotation, as the molecules are excited to higher and higher rotational energies, what's going to happen? So you can think about this as we go to higher and higher states. So imagine things are rotating around our molecule, right? As we go to higher and higher energies, right? That's the same as drawing, say, these concentric circles, right? They're going to rotate faster. As the radius becomes higher, they have to spin faster. Now, as they spin faster, we know this just pure mechanics, they're going to have an increase in centrifugal force. And this is going to push out on the molecule. So within this cloud, they're going to start adding an extra force on the molecule. And it increases the average bond length. So remember, so we have these things rotating, right? Not only vibrating, but they're rotating about some central mass. As you start exciting and pushing things to outer, the electrons are going to higher and higher orbits, and they're going to spin faster and faster. We have to conserve energy, and therefore they're going to store it, and they're actually going to increase that bond length. Okay? And so what this does, if the average bond length increases, okay, but that's only when you're in the higher energy levels, then it, quote unquote, distorts the spacing on those potential energy diagrams, okay? So now instead of having nice even spacing between rotational levels, you end up with the spacing that, like those vibrational levels are getting closer and closer together, the rotational levels that get closer and closer together as well. And now we have a correction, which is the distortion coefficient. You can derive this. But what you end up getting is now we have our our term bj of j plus 1, and then we'll have dj squared, j plus 1 squared, where de is also just another constant. Okay, so we've considered vibrational and rotational motion separately, but the thing to think about here is that rotational transitions are only on the order of a wave number, vibrational transitions are on the order of 1,000 wave numbers. In this manner, the rotational levels end up being, as we've seen on the graphs, they're superimposed on the vibrational levels. Okay? So what you end up having is you have interactions between the rotation and the vibration. You have to have interaction between these two. And so we get something called a rho vibrational spectra. Okay? So for rotational motion, our rigid rotor assumption stated that the bond length between two atoms is fixed, but our antiharmonic vibration model shows that the distance between the vibration levels and the bond length decrease. So we can actually see they're a little bit at odds. The way we reconcile this is that we recognize that there's a relationship between the rotational constant and the bond length. This is just remanipulating B to get h over 2I, and then substitute in for the moment of inertia, we get 2 mu L squared. And then the rotational constant can also be written in what's called spectroscopic units. This is always a little bit confusing. We can take our BE, which is our rotational constant, and then write it in this manner. So that's just h over 8 pi squared c mu L squared. That's what's called spectroscopic units. Now, since our rotational constant now is a function of bond length, not now, we saw the previous equation, it is a function of bond length, then our rotational constant has to be dependent on the vibrational level. That's where I'm coming back to, where I had that blurb that said, we explicitly assume to do our rotational, we have this fixed bond length, but our vibrational model showed that this is not quite the case, right? So what we do is we correct and say that at each vibrational level, we have a different vibrational constant, which is this, just from spectroscopic, just from known constants, Planck's constant, all of these geometric properties, meaning geometric terms of the two masses. And then we have an anharmonicity correction factor, okay? And that's this alpha. Again, another constant, but vibrational level specific. So again, the same way as that we now have at the vibrational level, the spacing's changing, and we had to have that second anharmonic term on the vibrational term. We now have a second term embedded here in our rotational constant, and this is also within having distortion of the rotation as well. Okay? So the spacing between rotational levels decreases at higher vibrational levels. So again, just thinking back, as we go to higher vibrational levels, the spacing between vibrational levels decreases, but also the spacing between the individual rotation levels increases. So both of them are getting kind of squished together. So the spacing between discrete rotational lines is decreasing. And so what we also, again, because of this, we end up getting unequal spacing between the rotational levels. Okay? So let's put it all together. So everything that we've done so far, this is the energy at any vibrational level, any rotational level, any Vj. We have a harmonic oscillator and harmonic correction. We have our rigid rotor solution for the rotation. We have centrifugal distortion. And then we have what's referred to as rho vibrational coupling, which is this extra anharmonic correction factor, okay, for the rotational states. So right now, you know exactly from all of this, you can now calculate where any line is in a rho vibrational spectrum. Not electronic transition yet, but just in a pure rho vibrational spectrum. And if we can predict their position. We can't predict their magnitude or their population. We'll do that later. But using the selection rules, we actually can predict where these locations would be in a like infrared or a microwave spectrum. Okay. So kind of the selection rules, if we look at these, they're called, any selection rule plus one is called the R branch. J minus one is the P branch. If it were a 0, we would have Q branch. As we get more satellites, which we get for electronic transitions, we'll have S and R branches. But if we use these two and we use our selection rules, all we have to do is look at this energy right here at 1, J plus 1 minus 0, J. All we're substituting in our, hopefully you see that, all we're doing is substituting our selection rules into here. As we do that with these known constants, you would actually find the position and wave number space of each one of these. If you've noticed, this is the central band. This is where it would be a Q branch if such a thing existed. They don't exist for pure row vibrational spectroscopy. So you actually see the R branch and the P branch. Okay? Now they're unequal in intensity. We'll talk about that in the next lecture. And they're also unequal in their distribution, and that's the population of each rotational line and each vibrational line. That's dealt with Boltzmann factors. But hopefully you can appreciate from this analysis, you now can calculate, because all of these are constants that are known, you can calculate where each one of these lines are. Okay? What's commonly done, though, is that these constants don't show up out of thin air. What you actually do is you measure the spectroscopy, and then you determine the constants. And then people write an infinite number of papers on how they determine the constant. They determine the antiharmonicity correction factor. That's paper 1. Paper 2 is the rigid, is the centrifugal distortion paper. My point is that you go and measure the spectroscopy and determine these constants. So things like CO, CO2, all these things are well known, where we know exactly where their position are. When I say exactly, as much as we can exactly know. So this is kind of how, when we say spectra, this is kind of the theory, the background behind it. They're related to the energy difference, okay? So that what you tune the laser to, or you tune your light source to, has actual meaning based on the structure of the molecule. And you can see basically here that this is going to always be species dependent. Of course, all these constants vary from species to species. Now, that was for a given electronic transition. There can also be rotational vibrational transitions during electronic transition, moving from one transition to the other. And the energy distribution function changes everything. Well, it changes and it complicates everything, okay? This is not nearly as nice as the pure rotational vibrational spectra that we just looked at. So let's take a look at NO. This is in the infrared. This is beautiful, right? This is in the UV. Still beautiful, but a lot more chaotic, okay? You have the interaction between the electronic states and the row vibrational states complicates the structure immensely. This is down at 226 nanometers, and this is way in the infrared. So the next step is to examine the electronic states and how they couple. Now, we won't be able to be as clean and precise once we get into the electronic states, but we'll be able to make some comments. The other thing is that the rules, as I'll say in a bullet point, if you notice, we had a certain set of rules for the row vibrational states. Do this, do this, do this, do this. And if you were taking a course like we're teaching, these would be like homework. Calculate the CO, the position of all the CO, and you would go through and you do that. And I'd say follow the same thing for ammonia or something like that if you're in the row vibration. You would be able to do it. You'd write a MATLAB code. You'd be happy. They'd be stick spectra right now, but you could put all the positions. Then we would give you how to do the population, and you would get everything look like this. When you go into the electronic structure, everything changes on a pure molecule basis. So everything's known for these molecules such that you can predict them, but they don't follow a standard set of rules. Everything sort of changes. Okay? All right, so let's talk about, if you notice on those potential energy diagram, the energy gap is very large to go from one transition to another. So that usually corresponds to visible or usually UV light. It's difficult to calculate the electronic states. There are ab initio solutions, but typically they're measured with spectroscopy, and then you end up assigning it. Again, the lowest level is the X state, and the electronic states typically go A, B, C, etc. Okay? The spectroscopic constants are different for each electronic transition, so they don't, even for a molecule, they don't stay the same. And there are certain rules governing electronic transitions, but they're different for each molecule, so it's very difficult to generalize. So let's look at, again, OH, another set of potential curves. What you can see is actually when we're going from one transition to the other, the actual shape of this potential well is different for each transition. What that means is that each one of these has a different electric potential distribution function, and then they all have different vibrational rotational constants. So this electron transition has all different constants than this, okay? So everything that you learn about this is not necessarily applicable for here. Okay? And now there are many electrons as well. When we were dealing with just pure the nuclear solution, we just have 1, 2 for diatomic. But now we have many electrons, and we have to account for their cumulative behavior. Really, what we want to kind of do is describe how they couple. And even what I've added in here is a bit difficult to digest, just I think on kind of first glance. If you haven't had a spectroscopy course yet, when we start talking about the coupling between spin and the different Hund's cases, they can be a little confusing. So just keep in mind what we're trying to do is just kind of understand how these things couple. So we have the energy of the electrons, and in particular, we're interested in the angular momentum of the electrons. Okay, so remember, just in addition to nuclei and nuclei, we have all these electrons, and they're spinning around really fast, right? So they have to generate an angular momentum. So here's a depiction. We have mass 1, mass 2. Okay. Now we have the orbital angular momentum around the internuclear axis. This is going to be L, so this is what's spinning around the internuclear axis. And we have a component along the internuclear axis that we'll call lambda. Okay, lambda, let's see, lambda controls how the electronic and the nuclear modes couple, and we'll talk about that. Now, lambda can have two directions, right? We can go left, right, and that's something called lambda doubling. And this can lead to degeneracy or splitting. So degeneracy is when the levels, basically what you can find is the same energy level has two different states, okay? And then when it splits, a degenerate level can split, where if you instead you have one degenerate level, it can go to multiple states, multiple discrete states where you used to have a degenerate. And this is usually done by being induced with some external field. So you hit it with a laser, some degenerate state will end up splitting into multiple states. Okay? And all of this is just nomenclature. So then we have to account for, in this manner, if we have splitting, meaning that some degenerate state goes to multiple states. So we originally only had one state here, and that branches off to two additional states on your potential. We then now have to keep in mind these new states and that they have some level of angular momentum as well. And this is called spin. I don't know why. I should go back and look why it's called spin, but electrons don't actually spin, but it was called spin. So again, it's just the extra angular momentum that's coming from the splitting of these lines. So again, all this is that, again, I told you this is kind of complex on what happens. And this is pretty simple molecule OH. So to keep in mind so that we ultimately can get a good formulation is we now also have a component of the spin along the internuclear axis. We'll call that sigma. So that our total electric orbital plus spin angular momentum. So think about this. Our total, if you will, angular momentum along the z-axis we'll call omega, and that's going to be lambda plus sigma. Okay, so hopefully this diagram kind of tells you all the different components. So ultimately what we're wanting to do is look at this angular momentum. Okay. Now, when the electronic orbit couples to the internuclear axis, it changes the rotational contribution. So you've done all this work to get these rotational contributions, but now when the electronic orbit couples to it, it changes everything, okay? And so depending on how it interacts, these are two cases, well, there's multiple cases, these are called Hund's coupling cases. Okay? So remember, before we brought in the electronic avenue, we had this rho vibrational interaction. And if we now consider that we have this electronic contribution, depending on the way it couples to the internuclear axis, this will change what your spectra looks like. So we'll only consider two. There's Hund's case A, which is a weak interaction between the electronic angular momentum and the nuclear rotation. And then so we have that L and omega are weak. Okay? So in this case, you end up getting that the total angular momentum is L, the nuclear solution plus omega, and then the appropriate quantum number J is L plus omega, and the rotational energy looks like this, and then it has this perturbation here due to this angular momentum contribution. Now, if we have Hun case B, again, I don't expect you to memorize. You have the information. Go back and look at them. If you have Hun's case B, we have no coupling of the spin and electronic orbital, but the spin couples to L, and we end up with a new, completely different angular momentum, N, okay, which is L plus lambda, and then now our total rotation is N plus S, and that should be our quantum number, okay? So Hun's case B is typically what we'll see in flame-generated radicals, except for very low rotational. This is where another level of complication. If you take OH, for example, it's Hun's case A for rotational levels like J is equal to 1 and 2, but about that it transitions to Hun's case B. Okay? So again, as I told you, the rotational energy formula is molecule specific, although it looks like what we've seen before, there's nothing really clean to write. So let's look at example OH, Hun's case B. The formulations are different for every electronic transition, okay? Okay, so the rotational energies are spin split, okay? So remember, some of these are degenerate, so they split. So now we have to write the rotational energy as rotational energy in rotational 2, and it's only, what we're writing here only holds for OH. For the excited state, our spin number is 1/2. So the quantum number J is N plus or minus 1/2. And again, you can go through and write all of this. This looks very similar to what we've seen, but we don't, instead of writing J, we're actually writing N is the appropriate quantum number to write here. We have B, we have our distortion version. And then actually, because we have to write, we have a spin splitting constant. Okay? So we have to actually even write another correction factor. That's the excited state. For the ground state, it looks even different. Okay? And the ground state has even more terms, and it depends on how it's coupled. And so do this B case. Again, there's no reason to go through each term. What I want to point out is that the spectroscopy becomes quite complex. That doesn't mean that you can't keep track of it. You write in a code. It's just not as pure as the rotational vibrational spectra. Okay? And all these things are well done. People spend careers or spent careers characterizing these things. So they're all done. And I'll get to my take-home message of what you need to know for all of this. So there's selection rules. Okay? We don't need to go into every one of these things. But again, we have delta J plus or minus 1, delta J equals 0 for J is greater than 0. But again, if we have these weak satellite regions that come from kind of from a lot of these splitting processes, you get O and S. They're much, P and Q, remember delta J plus or minus 1. Q is delta J is equal to 0. Okay? But then we have these much weak satellite lines. Again, only occurring when we have electronic states. I think we're finally, right, there we go. And what we can see overall is that our situation is becoming extremely complex. Okay? I wrote all this out such that you can use it as a way to say, okay, if I want to know more about the spectroscopy of a particular molecule I'm looking at because I'm not quite sure, I now have this kind of information. I can go into the literature and I can say, okay, what do I need to know? OH is all well known. Okay? So again, similar to the pure row vibrational excitation, we have our vibrational energy, which looks reasonable, except now we have another term. Okay? We have to have a higher order and harmonicity correction. But once we have all of these things, no matter how ugly they are, we can again predict where every one of these lines are. We can use our selection rules, put in our vibrational, rotational, and electronic energy states. And these are right here. This is comparable to what we did before. So when you add all of that together, you can end up finding the position of all your lines. Okay, and I'll have a take-home message in this at the end. Now, one thing that's useful is kind of a comment on spectroscopic notation. So you may read a paper and you see something that, hey, they tuned to the R16 line of the 1,0 vibrational band of the ADX system. And again, many of you will already have gone and looked what this means, but I thought I would provide kind of like a key for what this means. So an electronic state can be described by this kind of code, beta to the 2s plus 1, eta to the alpha. And where I've explained there, when beta is the valence electron level, whether it's the ground state or one of the excited electron states. 2s plus 1 is the multiplicity. Okay, it has the possible number of orientations, the total spin. So states with multiplicity of 1, 2, 3 are singlets, doublets, triplets. Okay, so, and then what you have, eta is the designation of the value of the orbital angular momentum. Okay, and these all have very classic spectroscopic notation. They go sigma, pi, delta for if lambda is 0, 1, and 2. Alpha is the parity. It's plus for symmetric wave functions. It's minus for asymmetric wave function. Okay. So really, one thing I do want to take a step back and say, what are these different Hund's cases or these different coupling cases? They're actually just explanations of observations. That's all they are. You saw something, and then you had to create a certain case to kind of characterize it. Okay? And then coming back to our nomenclature, this arrow just says what direction does it. Ground state to excited state. Vibrational band's easy. V prime, V double prime, you guys can use a break, so there you go. And then the final thing is rotational complex notation can get even worse. It's described by this beta to the eta alpha. Beta represents the branch, but it's just based on the selection rules. Eta is an integer related to Hund's case, so it's 1, 2, 3, depending on what Hund's case you have, A, B, C. Alpha is related to the lower level, and when eta is equal alpha, only one value is reported. So, kind of getting to the end of this, how do you read something like this? You've gone to the paper, you see this. Let me at least leave you with one bit of useful information. What you would say is that this R16 designates that you are in the R branch and that you're at the N double prime is equal to 6. So your quantum number is 6, and it's the N quantum number. Okay? Your vibrational, you're excitating from vibrational 0, level 0 in the lower state to V equals 1 in the upper state. And because we have electronic transition. And then we're going from the ground X state, which is a doublet with lambda splitting, and sigma equals 1. And we're going to, lambda is equal to 1. And then we're going to the A state, which has positive parity, and lambda is equal to 0. Again, are you going to digest this right now? No. But again, you kind of have some of you will. Some of you are really good. But what you have is kind of a key on how to go and read what this means. And it gives you kind of some information about the molecules. Again, all these details give you a background. Okay? But again, we've done all this for one molecule, and then they change for each molecule, and then often these rules are violated. Okay? So someone goes and finds something else, and then they go change. So we're not going to do any more spectroscopic details. Okay? We'll just show, these are actually some spectra. These are OH. These are CH, and you can actually see the kind of like doublets and triplets here. And then you can see NO. So again, what we can get out of this is different molecules exhibit different spectral signatures. This stems from the variations, all the variations in the coupling between electrons and the nucleus, okay, among other things. So finally, what I wanted to say is that the simpler models that are developed to describe the rho vibrational spectra and the IR work very well. Okay? When excitation involves an electronic transition, the simple models need to be altered significantly to match observed spectra. So again, I will save this kind of comment to the end, is that really what's happening is when you have the electronic spectra, you take what you know from the rho vibrational spectra, and then you make a enormous number of fixes for observation, okay? Because there's just no generic model. Now, do you need to know all these spectroscopic details to perform an absorption or lift measurement? Absolutely not. You don't need to know any of these, right? For well-known molecules, follow established protocol, but at least you know the background, okay? But now, what happens if you get into spectroscopy or you find a new molecule or a molecule that's not well known? You'll need to know a lot about the molecule to know, one, where to excite, number two, what transition, so you know how to actually interpret the signal. We'll get into that with fluorescence. So if you have a new molecule or molecule excitation schemes that are not well known, you actually have to go in and learn a lot about the molecule. Okay, so that's it for basic spectroscopy. Told you it was a bit of heavy lifting for this one. But probably now is a good time to take a break. I can take any questions, but maybe I can take one or two before we kind of officially break, but we're at 4:20, so anyone have a question? Yeah.
I was just curious, how much of the spectrum electron spin if it was like a...
Oh, so how you're talking about how it couples to?
Yeah.
Yes. The answer is everything. Anytime you change it, depends on which way it's spinning and how it couples. So if you're asking, does it change the spectra?
Yeah, well, see, I was actually that, but also if you change the direction.
Well, these are defined in a right-hand coordinate system.
Yeah.
So when you say the direction, maybe I'm not quite understanding. So you can define the spin, but in the right-hand coordinate system, it's following one direction.
If we change the direction.
Oh, you're talking, okay, so you're talking about instead of using just, you would have to, because the vector, the momentum, again, I don't know the answer explicitly. What I would say it would have to, right? Because it's changing the vector, right, which is your quantum, which is giving you your quantum number, right? So I would think it would have to. I don't know the answer to that. So I mean, I would think that it would have to because it's changing the vector.
And then if it does change, then
certainly if it changes the way you couple to, which I think almost it would have to, certainly will change your spectra, because then the coupling will change the way that it ultimately ends up splitting. It's what you have to take into account the different spin and the different splitting contributions. So yes, the spectra should change. But those are, let me come back and say that it's almost a horse and cart. I didn't understand your question at first, so that's why. But what you typically do would be measure something complicated, and then you would go back and fit the parameters, right? So you shouldn't think of it as I have like a level of theory, and then I go back and see what would happen then. You measure the spectra, it is what it is, and then you go back and figure out what the spin numbers would have had to be. So that's how you know that, like for OH, it's spin plus 1/2, because you've determined that from the spectra, okay? Sorry, I was a little confused by Chris, so I'm sorry about that. Other question? No? Okay. Well, we'll resume. Let's see, it's 4:23, so we're about 10 minutes behind, but you get your full break. We'll resume at 4:40.